I'm starting. All right, ionic compound radiuses. Well, or I'm sorry, not ionic compounds, just ions. Ionic radii. What a fun name. So, with ionic radii, we're not going to talk specific trend, left to right or up to down. What we're going to say is, if something forms a cation, are they going to be larger or smaller than the neutral atom? Smaller because they lose electrons. Okay, and on the other hand, anions are larger. Okay, from there, we want to talk about numbers of ions. So for instance, something that has a +1 charge versus something that has a +2 charge. The higher the positive charge, the smaller the atom will be, right? With ions that are negative, the higher the negative charge, the larger the ion will be. So the more electrons you gain, the bigger you get. The more electrons you lose, the smaller you get. Okay. Next trend was ionization energy. And one big thing I do want to talk about is something from your test, which is the quantum leap. Some of us actually stated quantum leap and talked about why it costs so much more energy to remove an electron from something that has a noble gas configuration. And some of us just kind of tiptoed around the idea that, well, removing another electron is harder. Well, yes, but the reason why it is harder to remove an electron from something that has already lost one is only if that specific thing is ready or already has a noble gas configuration. Lots of energy required to remove from a noble gas configuration. Ng means noble gas. Okay. Some of us were confused on this. This wasn't worth anything on your test. I was looking for the ionization equation. That was like one of the last questions on the exam 3. Part A said to write out the equation for the ionization of the first electron in sodium or in potassium, depending on what you had. This is what I was looking for, but I didn't grade it. I only saw a couple of them that looked kind of correct, and so I left that out. I made the description in part B worth 2 points instead. Okay? If I'm trying to remove an electron from the second, right, so this is my first ionization energy, and this would be my second. Remember we talked about how ionization energies could have first and second and third and fourth depending on what electron you're removing and how many you've already removed? Okay. So there was that. Talk about what an ionization energy is and what the trends are. So what was an ionization energy? E required to remove an electron. When we talked about the trend, we only talked about the trend in the first ionization energy on the periodic table. Okay. As we move left to right, does it get easier or harder to remove the electron? Moving towards fluorine. Harder. So ionization energy increases left to right. Why?
Because as you go to the right, it wants to gain instead of lose.
Likes to gain. Okay. What other reasoning could you give me? Really cool concept. Fluorine is the most electronegative. Okay. You could give me an atomic radius based explanation. As you move left to right, atomic radius goes down, right? And so since things are closer to the nucleus, harder to pull off because they are very attracted to the nucleus. Comes before the S. Okay, so there are a lot of reasons you could give me as to why the trend is what it is. All right, as we move top to bottom. What do you think? I hear decrease. Who agrees? Yeah. Yeah, absolutely. Why?
Because it gets further away from the nucleus, so it's easier to pull.
Further away means less attraction. Less attraction means easier to break. It's like we're back learning this for the first time again, where everybody's like, yes. It wasn't that long ago. I know there's a lot of information, believe me, I'm aware.
A lot of stuff happens since we did this.
Just remember, there are 11 chapters. I can feasibly ask you 3 to 4 per chapter at this point. That would give me 44 questions on an hour-and-a-half long final exam. So put as much energy into some of these chapters as you possibly can. Put more energy into the ones you're really worried about, because if you're worried about it, it means you probably haven't studied it as much lately. Yes? Didn't we just say?
44.
Like 44? Some of them will be multiple choice. Some of them will be short answer formula type questions like you've seen before. Anything on a previous quiz or test is fair game.
Can we get like market essays?
Not like, I mean, the only essays I could possibly ask you are of this chapter. You will be asked to explain a trend. I'll tell you right now that you will be asked to explain a trend. I will ask you to tell me what the trend is as you move left to right. I will ask you what the trend is from top to bottom on something from this chapter. You are warned. Yes.
We just do a little bit.
Oh, that would be so sweet. No.
Dang. That hurt.
The opposite of ionization energy is electron affinity, which means what? What is it?
The ability to gain electrons.
So this is going to be yes, but specifically an electron affinity is the energy released or absorbed when a neutral atom gains an electron. So we talked about electron affinity as a favorability concept. So we're going to talk favorability. We're not going to say decreases or increases because these numbers are all over the place. We're going to say it becomes more or less favorable as we move from one direction to another. Okay. As we move from the left side to the right side, does it become more or less favorable to gain an electron?
More.
Think about it. Things on the right side have what kind of charges? Negative or positive? Negative. Things on the right, 15, 16, 17, all have negative charges, common negative charges. What does that mean as far as gaining electrons? Do they have to gain electrons to become negative? Yes. In order to become negatively charged, you have to gain an electron, right? So as we move left to right, it becomes more favorable.
confusing myself.
The values, when you look at electron affinity in your book, the values become large and negative. Negative means favorable on electron affinities.
Just remember fluorine.
Yeah.
Things around fluorine. And that's
They kind of follow the trend of electronegativities. So, all right, from top to bottom.
that's what I read.
Anybody remember what we said about electron affinities, top to bottom? We said they're kind of the same. If anything, they get a little bit more favorable. They kind of get better. I don't write the term kinda on my board very often, all right? Kind of favorable, meaning there isn't really a huge difference as you move top to bottom, and there are definitely groups that don't follow this particular, well, it should get more favorable as we move down, okay? But in general, as a trend, we can say kind of favorable. All right, what's this? Let's talk electronegativity real quick. All right, electronegativity. What is it? All right, electronegativity is going to be a measure for an atom's ability to attract electron density towards it. We say electron density because a lot of times we use electronegativity to determine if something is polar or nonpolar. We try to determine if a bond is ionic, polar, nonpolar, depending on the electronegativity differences between two values. And this comes into play in our next chapter, which is chapter 8. What is the trend for electronegativity? Left to right? Increases.
I know this one.
Top to bottom? Decreases. As I tell my sophomores, the fluorine is the X on the map. The closer you are, the more electronegative you are. The further you are, the less electronegative you are. Everything decreases as you move away from fluorine. All right.
It's too bad they didn't make fluorine. They didn't rename fluorine something with an X.
Man, my arm hurts. Can I? Hang on. Woo. Chapter 8 was a very reviewy. Very, very reviewy. Chapter 8, we covered Lewis structures. Something you probably feel okay with. Chapter 8 also talks about the types of bonds. Chemical bonding. Specifically, ionic, covalent, metallic. Ionic bonding, of course, being the electrostatic attraction between two ions. Covalent bonding being the sharing of electrons in a bond. Can be polar or nonpolar in nature. Metallic being metals in a sea of electrons. Complicated type of bonding we are not discussing in great depth. All right, from there, lattice energy. We said that with lattice energy, as charges increase and sizes decrease, lattice energy gets stronger. So, the larger the charges are, positive 2s, negative 2s are going to be stronger than positive 1s, negative 1s. The stronger the lattice energy is going to be because the stronger the attraction is going to be between something that has double the charge. The smaller the ions are, so if you have really small ions, say a negative 1 charge and a positive 3 charge, you're going to have pretty small ions. Those things are going to be more attracted because they can get closer together. Yes?
What does that say?
Which one?
The metallic one?
Metals in the sea of electrons. A very odd form of bonding, if I say so. All right. The covalent discussion. Lewis structures. Who wants to draw a Lewis structure? Okay, cool. CO2. How do we draw a Lewis structure? What do we start with? How many electrons do we need?
16.
I'm bad at math, don't judge me.
4 for carbon, 6 for each of the oxygens, times 2 is going to be 16. What goes in the middle? The least electronegative. We bond everything with a single bond first, then we try to fill the outer octets. How many electrons do I have in my structure right now? 16. Can I add any more? No. What do I do instead?
Create double bonds.
Right, because carbon doesn't have a
Okay.
have an octet, right? So we're going to make a double bond. We're going to make a double bond. Now does everything have an octet? Yes, it does. Formal charges. You've done it before. We do valence electrons of the atom minus the number of dots plus lines around that specific atom. So for this oxygen, how many valence electrons did this oxygen give to our structure? 6. Minus
6.
2, 4, 5, 6. So this particular atom, oxygen on the left, has a 0 formal charge. Does this oxygen have the identical same situation? Yes, it does. So do I have to do the math twice? Nope. What about this carbon? Carbon should have 4 minus 1, 2, 3, 4. 0. Is this a good Lewis structure? Why? Because the formal charges add up to be 0. See this one?
Nasty.
Does it have 16 electrons?
Yes.
Yeah. Does everything have an octet?
Yeah.
It does. So is this technically a viable Lewis structure for this particular compound? Yes. But we would not pick this one. And it's because we're going to calculate our formal charges. So again, the carbon still has a 0. This oxygen has a negative 1 charge. This oxygen
Plus.
has a plus 1 charge. We do not want charges if we can avoid them. So that one does not work. All right. Oh, we gotta talk resonance too. Resonance and polarity were other big concepts in this chapter.
Everything else is blurred.
I know. It's been a long semester, right? All right.
Nobody likes nitrogen.
19.
It's a black sheep of all that. It's just
All right. So when we talked about resonance, we had structures like this.
Please don't make us write.
Putting the double bond here, is this any more viable than it would be here? Or here? No. So we had to learn to draw all of them. And one of the big questions from the exam that several of us did not remember was the impact of resonance on polarity. What does resonance do to bond length? It evens everything out. Everything in this structure has the same bond length because that double bond is moving from place to place to place at a pretty fast speed. So when we measure the bond length, resonance evens it out. So in this particular case, all of these things would have somewhere between a 1 to 2 bond length, right? All of these different angles or all of these different bond lengths can be measured to be somewhere between a single and a double bond, but they would all have the exact same number. So if we said that this one was 1.7 angstroms, this one would be 1.7 angstroms, and this one would be 1.7 angstroms. Because resonance evens this out, and there is no double bond or no pair of electrons on the center atom, this would be a nonpolar structure. Everything is evenly pulling on the nitrogen. What we should actually draw is something like this.
We can do that.
That little dot means that there is an implied double bond in all 3 locations at the same time. That's what the resonance does to a structure.
You want us to do that?
Ready for the... No, that's what we're saying it should look like. And I drew it that way for a specific reason because the next topic we talk about in chapter 9...
Wait, why did the bottom 2 have 5 dots and the top one have 8?
I still don't have those memorized.
What
Say again?
is the top one only have 4 and the bottom 2 have 5? That's boogie.
I definitely did. The only thing I knew was bent and
Okay, thank you.
I wrote bent on my test.
Our next one,
Wrong.
it is not bent.
Yeah, what was the answer?
Trigonal pyramidal.
That's what I wrote.
You're talking about the tetrahedral structure?
Oh, yeah, that was the one I was
referring to
talking about.
4F.
Are you talking about the tetrahedral structure or are you talking about the trigonal planar structure?
Can we go?
Because this one, how many domains? Hey, shush! How many bonding domains? 3. How many non-bonding domains? 0. 3 bonding domains means trigonal planar. 3 bonding domains with no electron domain geometries or no electron domains means that the electron geometry and molecular geometries are identical.
If there's a lone pair that doesn't make it bend.
Be driving down the street.
If there was a lone pair instead of an oxygen, then it would be bent.
Hold on. I'm going to draw that one because you're all not seeing it in your brains. This is the one you're talking about. It looks something like this. It was like the SO3 molecule. Yeah. The SO3 molecule does, in fact, have a lone pair, but there are 3 things bonded to it, not 2. A bent structure only has 2 things bonded to the central atom.
Wait, what is that one called then?
That's pyramidal, trigonal pyramidal.
Yeah, right.
Because it's in the shape of a here.
'Cause it's a
You see the bottom part
Yeah.
is the pyramid?
Yeah, I know. I can see the picture of the 3D molecule. I just forgot the name.
Chapter 9. All right. Let me double check that we're not. Hold on.
Molecule, and I see the
Real quick.
3D, and then I see the 2D.
All right. Before we move on to chapter 9, polarity. Polarity in a molecule. Polar or nonpolar? Nonpolar. Do you see the symmetry in the molecule? Yes. Polar or nonpolar?
Polar.
Polar because of the lone pair on the central atom. A lot of us said polar because of the lone pair, but then you drew something, guys, you drew something that had like 17 lone pairs. So you have to say polar because of the lone pair on the central atom that affects the other atoms on the central atom. Be more specific is what I'm saying. Okay? All right, along with the term polar, we introduced the idea of a dipole moment. What does that mean? What's a dipole moment? Go ahead.
Where it's pulling on the central atom.
Right, so it's like the direction, if you will, of where the electron density is mostly located. So we draw things like that. We would say that this one has a dipole moment that points towards the lone pair, because the lone pair is the most electronegative thing in this structure. Okay? Dipole moments were things that we could draw between two atoms as well. What we would do is we would point toward the thing that had more electronegativity. What we're indicating in something like this is that this one is more electronegative, so it would hog all the electrons towards it in a bond. Okay? And likely this would also be an ionic compound, but still. Remember that we talked about the spectrum of ionic, polar, and nonpolar, and we used electronegativity differences that range from 1.1 up to whatever, or 1.7 or greater was ionic. 0.3 to 2 is polar, and anything below 0.3 is nonpolar. Remember those differences. If you are asked to do something with that, I would give you the ranges. Okay? Woo-hoo. All right. So that was chapter 8. Bond enthalpy. Sorry. I lied. One more thing that we learned in chapter 8 is how to calculate delta H using individual breaking and forming of bonds. This is number 2. Number 3, sorry, on your exam 3, number 3.
What letter?
Just go to number 3. They're identical. In number 3, bond enthalpies. Most of us got it, some of us didn't. That being said, bond enthalpies.
This isn't that bad. It's all chart.
Another way to calculate the delta H of a reaction. The third way that we've learned, we had Hess's law in chapter 5. We had the individual reactants and products in chapter 5 to calculate a delta H of reaction. And here we have the delta H of reaction by bonds broken minus bonds formed. In order to do this, you'd have to have the table of values for each bond broken. All right. I'm gonna write that down for you. All right. Chapter 9. Geometry. Who?
Oh no, I don't think that was good for chapter 2.
Vesper theory is where we focus most of our efforts in this chapter. Vesper theory is the fancy term underneath the umbrella of Vesper theory. We learned electron domain geometries with bond angles. Underneath this umbrella, we also learned molecular geometries with bond angles and the ones that are affected. We learned hybridization underneath the Vesper theory. Yes?
Can you explain number 6 on the exam?
Sure. For the difference between the first and second ionization energies?
Yes.
The first and second ionization energies have that quantum leap. So the first ionization energy is the energy required to remove the first electron for any of the group 1 metals that you're given. The second ionization energy of that would mean you have to remove an electron from its noble gas configuration. And that's completely unfavorable, because remember, everybody wants to be a noble gas. So you're removing an electron from a full octet, essentially.
Yeah, like how would you write the
Oh.
equation?
I did that on the board. Hold on. I'll show you. For N or K? Do you care?
I had K.
So K. That was it. Because you're removing an electron and creating an ion.
Okay, I see.
For Na, same thing. Energy required to make this transition is what you were.
And then, okay, so then for B, when it says propose an explanation for the difference.
Yep.
What would
Well, so the difference is what they're saying is the difference between.
is the
There's like one of them is like 495 and one of them is like 4950. 10 times higher because of the electron configuration would be. You'd be removing. So if you think about like Na plus, okay, that looks like a noble gas, right? It has the configuration of neon. If you're trying to remove an electron from neon, that's hard because it's a noble gas. It doesn't want to do that. It likes its electrons. Very, very, very stable. You're trying to unstabilize a noble gas is essentially what you're trying to do.
Will that be on the phone?
Like I said, there will be questions about at least one of the trends. I will ask you to describe them. That is a very fair question for a final exam as far as like, tell me the difference. Why is the ionization energy of a first electron being removed so much smaller than the second one for this specific atom? The quantum leap is the answer, yes. Because the difference is you're trying to remove an electron from the noble gas in the second one than you were in the first one.
So like instead of if I just wrote quantum leap and nothing else, that would still be right?
No, you have to explain. I mean, I would never be like, okay, just tell me one word. Why? I would ask for an explanation. Okay, so hybridization. Hybridization depends on which geometry, electron domain or molecular geometry. Yup.
Because that's what those are.
Yes. So some of us on our test wrote this. It was a tetrahedral structure. You even wrote tetrahedral, but then you wrote sp2. You should have written sp3.
Well, but I put triple flame.
You all had different, like, compounds, right? Like, there were two different versions of the exam. Different compounds, but all of the answers underneath it should have been the same because your compounds came out to be identical. Like, some of you had PO3 3 minus, and the only difference between the PO3 3 minus and the SO3 2 minus is that the PO3 3 minus had a formal charge of 0 on the central atom, and the SO3 2 minus had a 1 on the central atom.
It's amazing that you remember that difference.
Oh, yeah. Okay. What else is under Vesper theory? Sorry, I got distracted. Bond angles. Well, we're going to go through that. Like, I'm going to go through and I'm going to make the chart up through tetrahedral like I've done before. I'll make that for you. I just want to get through other topics in chapter 9 because if I have to do that, I can do that tomorrow too. All right, from there, other things under Vesper theory. Sigma and pi bonding. We introduced sigma bonding, which is overlap that's head-on. So either two s orbitals overlapping, they only can overlap in one point, right? Whereas p orbitals can overlap in 2 points if you put them next to each other and they line up like this. But the ways the p orbitals can overlap is like this, with the lobe up here and lobe down here. 2 points of contact, you can also overlap them in a sigma way. And so this led us to MO theory. But for now, sigma bonds, overlap that is head-on. Single bonds. 1 sigma. Okay? Pi bonds. 2 points of overlap. I'm going to reference you to your book to look at those diagrams again if you're confused on what we're writing up here. 2 points of overlap, a double bond, has 1 sigma and 1 pi overlap. Triple bonds, have 1 sigma and 2 pi overlaps. Okay, so that was under Vesper. Do-do-do-do. Look, I'm making a concept map, guys. That doesn't belong. It's my concept map. Okay, that was all under the heading of Vesper theory. Then we introduced a new theory. Again, these are all bonding theories. 3-dimensional bonding theories, if you will. That's all I need. All right. MO theory, MO diagrams. This is number 5. Remember these diagrams? Most of us did very well on this. Most of us did very well on them.
Most of the thing is how long it takes to draw.
Yeah, no joke. Sigma, 2p, pi, 2p, pi, 2p, antibonding, sigma, 2p, antibonding. All right, the 2s2p one, was that NF? Some of you had PCl and these said 3p and 3s. Some of you had NF, which said 2p and 2s. So we're going to do NF. What's your first step? Yeah.
Before we do that, do you think we should know how to draw that?
No, just how to fill it in.
Okay.
So you gotta fill up your 2S.
How I can do this on an exam on Canvas is I can give you the diagram on a piece of paper, right, for you to use, and then I can ask you questions about it like I did on it. I would just ask you the questions and ask you to put in, what's the bond order? 2. What types of bonds are present? And have you like select the ones that are present. All right, what do we do first? Sorry.
Oh, fill up the 2S orbital.
Yep. So we're gonna look for the electron configuration of the atoms, right? And we're gonna fill in the s and p's on both sides. So for n, we do 2s2, 2p3. Why are we ignoring the 1s2 that it starts with? Because it's like way down here, right? They're shielded, they don't count, they're not going to involve themselves in bonding. Okay? 2p3. F is 1s2, 2s2, 2p5. Again, no 1s. Okay. What do you do next?
Fill in boxes.
Fill it all in. 1, 2, 3, 4. 3, 4. Remember, you have to fill one box before you can move to the next level. Remember that you're also filling your boxes one at a time. That was something that some of us didn't do right, but I still gave you a point because you did most of the other stuff right. 3 on this side, 5 on this side, total of 8. 2, 3, 4, 5, 6, 7, 8. Okay, bond order. So we're going to count the number of bonding electrons. 2, 4, 6, 8. Antibonding electrons. 2, 3, 4. I made a bond order of 2. What does that mean?
Double bond.
Double bond. That's what that means. It means there's a double bond. The next question. How many and what types of bonds? I had some people tell me a double bond. That's not correct. What am I looking for here? How many sigma? How many pi? I had some people tell me more than 1 sigma, but I do want to remind you that in order to figure this out, you have to go through and you have to cancel out any bonding electrons with antibonding electrons. So down here, these two cancel out these two. There is not a sigma 2s orbital overlap in this particular bond. That cancels that out. So, doesn't count. All right, up here, these two pi antibonding electrons, each one is going to cancel out 1 pi. Why did I choose to cancel out one whole box? Because the full box means there's a pi overlap. This is just visualizing what's happening here. In reality, you would cancel out 1 on each box. But for visual purposes only, 1 pi bond remains, correct? 1 sigma bond remains. If you wrote 1 sigma and 1 pi, you got it correct. Para or diamagnetic? Paramagnetic. Because these still count when you're determining magnetism. Paramagnetic means unpaired electrons in the highest occupied molecular orbital. See you tomorrow. That was like 90 minutes of me talking.
Yeah, I know.
Yeah, it sucked. I was here. I don't do this for most classes.
We're special.
You're special because I want you to pass your final exam, yes.
I mean, I won't have
So boy, am I going to be a disappointment then.
I'm glad we can agree on that.
Goodbye.
So Bishop,
I love you all. Have a great day.
so you know how we can only use
I don't want to talk about chemistry anymore.
so how we can only use one sheet of paper.
One sheet on the front side, 8.5 by 11.
What if we folded it into a little booklet?
Why would you do that?
2 booklets to keep more organized.
Have a great day.